So in the earlier lecture I talked about the Dirac's Hamiltonian, and now I'm going to talk about the matrices alpha and beta which are there in the Dirac Hamiltonian. So let us try to evaluate these alpha and beta. So since we know that this H Hamiltonian is equal to C alpha dot P plus beta m naught C square, but you can write down it as this H is equal to C can be taken outside plus beta m naught C. So let me go to the Klein-Gordon equation now again. So according to Klein-Gordon equation, as we have evaluated the Hamiltonian is equal to plus minus C, it is px square py square pz square plus m naught square C square under the root. That's what we have evaluated, and from here I can calculate H square is equal to C square px square py square pz square plus m naught square C square. So I can write down it as H squares upon C square is equal to px square py square pz square plus m naught square C square. So let me call this as equation number 7, because I am continuing it with the earlier lecture. So that means if I try to look at this part, then from here I can calculate this H square upon C square. H square upon C square is equal to alpha dot P plus beta m naught C, its whole square. And let me try to simplify it. Alpha x p x alpha y p y plus alpha z p z plus beta m naught C, its whole square, and say it is equation number 8. And from here I can calculate this H square upon C square, and let me simplify it. So it is alpha x square, if I open this, px square plus alpha y square py square alpha z square pz square plus beta square m naught square C square plus alpha x alpha y plus alpha y alpha x px py plus alpha y alpha z plus alpha z alpha y py pz plus alpha z alpha x plus alpha x alpha z pz px plus m naught C, it is alpha x beta plus beta alpha x, it is px plus m naught C alpha y beta plus beta alpha y, it is py, that's what, and plus it is m naught C alpha z beta plus beta alpha z, it is pz, and let me call this as equation number 9. Now if I compare this 7 equation and 9, then the coefficients of px square py square and pz square, it is always 1. So if I keep this in mind and compare this particular equation with this equation, then what I am getting, and this is m naught square C square, here it is m naught square C square. That means if I compare this, then beta square is equal to 1 and px square it is px square, means alpha x square should be equal to 1, alpha y square should be equal to 1, alpha z square be equal to 1, and rest of the coefficients will be equal to 0. So that means if I generalize this idea, then what I am getting, let me write down this. So comparing 7 and 9, what I am getting, that is alpha x square is equal to alpha y square, and which is equal to alpha z square is equal to beta square is equal to 1. Let me call this as equation number 10. And alpha x alpha y plus alpha y alpha x is equal to alpha y alpha z plus alpha z alpha y, which is equal to alpha z alpha x plus alpha x alpha z. It is equal to 0, and alpha x beta plus beta alpha x is equal to alpha y beta plus beta alpha y, which is equal to alpha z beta plus beta alpha z, and it is equal to 0. And let me call this as equation number 1. So this equation 10 and 11 suggest that alpha and beta, or I can say that alpha x, alpha y, alpha z and beta are said to be anticommute, and their squares are unity, right? That's what we are getting. So thus in general I can write down, that alpha I alpha j plus alpha j alpha I is equal to 0, and alpha I beta plus beta alpha I is equal to 0, and alpha I square is equal to beta square, and it is equal to unity. And here this I is not equal to j, and I and j are either 1, 2, 3, or sometimes we can take that as x, y and z, right? So these are the terms which I am getting. Now if they are matrices, then what should be their dimension? So next question arises, that what is the dimension of alpha and beta? So next is the dimension of alpha and beta. I will talk about it. Alpha and beta means, let me talk about the dimensions. So for this, since again consider that h is equal to c alpha p plus beta m naught c square, or c alpha dot p plus beta m naught c, but h is Hermitian. So if h is Hermitian, so that means h dagger is equal to h, or I can say that c alpha dagger p plus beta dagger m naught c, it must be equal to c alpha p plus beta m naught c. And if it is so, that means, what does it mean? It means that alpha dagger is equal to alpha and beta dagger must be equal to beta. So that means I can say that beta dagger is equal to beta and alpha dagger is equal to alpha. That's what I am getting out of this equation. Also, as I know that alpha square is equal to 1 and which is also equal to beta square. So that means alpha I is equal to, alpha I must be equal to alpha I inverse and beta must be equal to beta inverse. So that means both alpha inverse and beta inverse will exist. Means both alpha inverse or alpha I inverse and beta inverse exist. What does it mean? This means that alpha I and beta are non-singular, right? They're non-singular. And what does that mean? That determinant of alpha I must be equal to non-zero, and similarly determinant of beta, it also must be non-zero. So therefore let us recall again. Alpha k beta plus beta alpha k is equal to 0, means alpha k beta must be equal to minus beta alpha k. Now let me take determinant on both sides. Taking determinant on both sides, if I take determinant on both sides, then what I am getting? The determinant of alpha k beta is equal to determinant of minus 1 and determinant of beta alpha k, and I can simply, this can be written as determinant of alpha k, determinant of beta must be equal to determinant of minus 1. So determinant of beta and determinant of alpha k. So that means determinant of minus 1 means it is minus, or here it is 1, and here, because they will cancel out. So determinant of minus 1, that means that 1 is equal to minus 1 raised to power n. Here I have chosen that n is the dimension of alpha and beta, or alpha I and beta. So minus 1 raised to power n, this means that n is a even number. So that means n either 2, 4, 6 and so on. So these are the possible dimensions of this what we call alpha and beta, or the Dirac matrices. So first of all I will check whether polymatrices, now because we all of us are familiar with the polymatrices, so I will check whether polymatrices can be treated as alpha and beta or not. That's, I want to check it out. So let us recall polymatrices. So if I recall polymatrices, then sigma x is equal to 0, 1, 1, 0, and sigma y is equal to 0, minus iota, iota and 0, and sigma z is equal to 1, 0, 0, minus 1, right? So these are the polymatrices. So here sigma x, sigma y, sigma z are 2 by 2 matrices which are anti-commuting. Which are anti-commuting with each other. And their square is unity. That is, I can say that sigma x sigma y plus sigma y sigma x is equal to, if I put their value 0, 1, 1, 0, and then 0 minus iota, iota 0, plus 0 minus iota, iota 0, and then 0 1 1 0, and if I solve, then it comes out to be 0. Also, if I try to find out sigma x square, that is 0 1 1 0, 0 1 1 0, then it always comes out to be identity matrix, right? So it is 1, right? But we require 4 matrices, right? We require 4 matrices, and which must be linearly independent. So if I require a linearly independent matrix, then one choice we having is only the choice is 1 0 0 1 is the identity matrix. But, and it must anti-commute with sigma i's, but actually I commute with sigma I. So what we need, a matrix such that which must anti-commute. Commute with sigma I. So if it is, but it is commuting, so that means I it cannot be the 4th matrix of which fulfill our requirement. So that means idea of considering, it means idea of considering sigma i's and I as Dirac matrices, it cannot fulfill our requirement. It cannot fulfill our requirement. It cannot fulfill our requirement. So they can be neglected. So that means 2 by 2 matrix is not a choice, good choice for the Dirac matrices. So let us now choose. So let us now choose n is equal to 4, the least possible dimension of alpha, I and beta, means for the Dirac matrices. So to get idea about alpha I and beta, let us find trace of alpha I and trace of beta. So for this, consider alpha k beta plus beta alpha k is equal to 0. That means beta alpha k is equal to minus alpha k beta. Now operating with alpha k inverse on both sides, if I operate, then I can write down it as like this. It is alpha k inverse beta alpha k, it must be equal to minus alpha k beta. So sorry, just let me oh, I operated with it. So alpha k, alpha inverse alpha k beta, and it will become an identity matrix. So that means I can say that alpha k inverse beta alpha k is equal to minus beta, right? So let us do one very interesting trick here, and that's very interesting, right? Yeah, so as I know that I will use the idea that trace of ABC is equal to trace of CAB, right? So that means let me take the trace of alpha inverse beta alpha k, and if I use this property, then this can be written as trace of alpha k inverse and beta, and this will become identity matrix. So if it will become an identity matrix, then I can write down it as 1, so it will become trace of beta. But if I look at this particular equation, then it can be written as trace of alpha k inverse beta alpha k is equal to trace of minus beta. So from here I can write down it as trace of minus beta, right? I used this equation directly here, and here I have taken only one side, right? So if I compare these two, means from here I am getting that trace of alpha inverse beta alpha k, sorry, k should be there, it is equal to trace of beta, and here I am getting that trace of alpha k inverse beta alpha k is equal to minus trace of it is beta, right? Yeah, it's beta. So it is trace of beta. So that means this must be equal to this one. So I can write down this result as the trace of beta is equal to negative of trace of beta. So which implies that if I bring this towards this side, and it will be equal to 0. So that means twice will become 0. So that means trace of beta, it comes out to be 0. That's what we are getting. It's a very interesting result which we are getting here. And similarly, we can prove that trace of alpha k is also equal to 0. These are the two things which we have to keep in mind. Means alpha and beta should be chosen in such a manner, means alpha and beta, or alpha k and beta are chosen in such a manner such that their trace is equal to 0. Now the idea comes in our mind that can we use polymatrices and identity matrix to generate a 4x4 matrices such that their trace is 0, right? So therefore, if we choose alpha k is equal to sigma 0, sigma k 0, right, and beta as I00I, right. So if I use with negative sign, so that means if we take their trace, so here the trace is automatically 0, and here it is identity, it is negative of identity, then its trace is also comes out to be 0. So let me express this again. So alpha x can be written as this alpha x, it can be written as 0 sigma x 0, and it is equal to 0 0 0, and it is 0 1 0, sorry 1 0 0 1 1 0 0 0 0. So if I write down it in this manner, sigma y can be written as 0 sigma y 0, and it is equal to 0 0 0 0 0 minus iota 0, it is 0 minus iota 0, and similarly sigma z can be written, sorry not sigma but it is alpha, sorry, yeah, it is alpha y and alpha z, so it is 0 sigma z 0, so it is equal to 0 0 0, it is 1 0 0 minus 1, it is 0, sorry 1 0 0 minus 1 0 0 0. So if I try to write down it in this way, and beta I can write down as 1 0 0 1 0 0 0 0 0 0 0 0 minus 1 0 0 minus 1. So beta can be written in this way, right. So these are the matrices, Dirac matrices which we are getting, and they will satisfy the relationship because they must satisfy the relations that sigma x sigma, sorry alpha x alpha y, not sigma but alpha x alpha y plus alpha y alpha x must be equal to alpha y alpha z plus alpha z alpha x must be equal to y z, sorry it is y, and alpha z alpha x must be plus alpha x alpha z, it is equal to 0. And similarly we can, if I use these values, we can prove this result, and we can also prove alpha x beta plus beta alpha x is equal to alpha y beta plus beta alpha y is equal to alpha z beta plus beta alpha z, it is equal to 0. And we can also prove that alpha square means which is equal to alpha x square is equal to alpha y square and alpha z square, and it is equal to beta square, and it comes out to be unity, means identity matrix. So using these results we can prove these results. So this is all about the Dirac matrices, and they must satisfy these properties. So that's all for this lecture. In the next lecture I will talk about this probability density, right. So how probability density can you evaluate it? So that's all for this lecture.